Hi, I'm Matt Stack. I'm a solutions architect at NVIDIA, and I'm going to be talking about programming models for CUDA, but just more generally, the NVIDIA HPC SDK and a modern way to program for the NVIDIA platform. If I only had 1 minute for this talk, I would just say it's not CUDA anymore. Like, it's not just CUDA. There is a spectrum of ways you can program for the NVIDIA platform. And it's kind of like the opposite of the way it used to be, where it was just CUDA or OpenCL. And you can have like a range, like if you're very interested in portability, we have offerings for that in our HPC SDK, or maximum performance with CUDA, and everywhere in between. So yeah, this is kind of like the spectrum or the ramp going from left to right. A recent development is accelerated standard languages. So the International Standard Committee for C++ and also for Fortran. So this is writing completely standard code. And the like dream goal for this would be you are already using modern C++ or modern Fortran. Like you can see on the top left, you're using like std transform. All you would have to do is just add one extra bit and a compiler flag, and then you could run in parallel on your GPU or on your CPU. And then the same for Fortran a little bit below. And then in the middle, you have your directive-based languages, which you've heard a lot about before, OpenACC and OpenMP. It requires a bit more code change. Usually you have to manage your data and stuff like that. And then on the right, you have CUDA, which is your highest performance, but also requires the most code and the most time to get a performant implementation. But it is also the core. Like all these from the left to the right boil down into CUDA. So it doesn't matter if you're writing OpenAC or OpenMP offload. If it's running on the GPU, on an NVIDIA GPU, it boils down to CUDA. There's also a fourth option, which is just using our math libraries, which we'll talk about. And also there's stuff like AI is super important to NVIDIA right now, but I won't speak on it. And also quantum computing. You can ask me questions about that, but I'll probably have to defer you to someone else. So this is where you'll find all that goodness, the NVIDIA HPC SDK. You can see it has programming models, compilers, core languages. We'll talk about that in a little bit. It's called the CCCL, C++ Core Compute Libraries. It's made up of 3 parts. We have math libraries, BLOS, FFT, QRAND, QTensor, and then a bunch of communication libraries like MP, MPI, NVSHMEM, and Nickel, and then some profilers that we'll talk about tomorrow. There's a bunch of releases per year for this, so if you have any bugs, there's a number of people you can reach out to. And I'll link my email, or you can just talk to me in the breakout. And we have our HPC compilers. These were built on the PGI compilers, so these weren't just spawned out of nowhere. These have decades of experience. They're multi-platform, so x86, ARM for our, which is interesting for our like upcoming Grace CPU. So we're very focused on the CPU performance of our compilers. And then these are kind of dense slides. They're mainly for your benefit if you want to go back and read through them. NVIDIAns chair the C++ concurrency and parallelism group, the C++ library evolution group, and the US languages committee. So NVIDIA is very focused on implementing modern and performant parallel implementations into the standard itself. And again, you can read through this as you want. Similar, just some stuff in the pipeline for C++ 23 and beyond. A lot of people at NVIDIA are actively working on these, and our compilers are usually used as a test bed for these systems, so often they will be included in some pre-release before the standard for you to play around with. This is just a really simple workflow for using, we call it STDPAR, Standard Language Parallelism for C++. If you've used C++, I'm sure you've used CPP reference before. You just want to look for the algorithm that has execution policy. And then that just means it has an implementation where with the correct compiler flag, it has a parallel implementation on the GPU and on the CPU. And it's pretty easy. There's an example in the breakout session, but you just add in that one argument and then do some compiler flags to make sure it's actually generating the code you want on the GPU or the CPU. And then it should work as expected. But it's not just good for Hello World or simple for each. Lululesh has an implementation of completely ISO standard C++, and it is as performant as all the other ones, OpenMP, OpenSCC, CUDA, etc. If you have any questions about that, feel free to talk to me in the breakout room. And this is just a little sample of that. You can see on the right, boiling down to just writing completely standard C++, can save you a lot of space. And it's easier to maintain and read and completely portable. The NVIDIA compilers are usually the cutting edge in terms of implementing the capability of the standard as far as like portability and performance. So that's where I would recommend testing out these features. But the other vendors have implementations as well, I believe. I'm gonna rely a bit more on my notes for Fortran. So in ISO standard Fortran 2008, they added do concurrent, which allowed users to express loop level parallelism. When you compile with NV Fortran and use the compiler flag, it's called -stdpar, the compiler will automatically offload the do concurrent loop to either the GPU or the CPU, and all the data will be managed for you with the CUDA unified memory system. Just because there's no magic going on. It all boils down to CUDA in one way or another. The difference between do and do concurrent for Fortran is just the do concurrent is telling the compiler that there's no data dependency between the loops. So the compiler is free to execute the iterations of the loops at any time or at the same time. And the other interesting thing with NV Fortran is that there are some Fortran intrinsics that have a cuTensor backend. So things just like matrix multiply has a pretty simple way to replace it with a GPU backend that also takes it into account the tensor cores on the NVIDIA GPU. And we have an example in the hands-on if you want to play around with that. But it is pretty easy. You just include your module, and then the compiler usually takes care of everything else. And there's a compiler flag where you can have the compiler print out the information that it's looking at, so you can actually make sure it will say like, okay, I see some GPU performance I can optimize for, and I'll do so. So you can see what you're going to get when you run. These are similar examples to before, but you can just see on the left at the bottom just how easy it is to switch with the same code, one compiler flag to go from running in parallel on the CPU or the GPU. And if you have any questions about like what's going on behind the scenes, you can ask me. And it's just a flag switch between -stdpar equals multicore or -stdpar equals GPU. As mentioned before, we have a number of math libraries, anything you could want. All of them have great documentations and great teams behind them. So if you have any questions, feel free to ask. This is just a matrix of like which math libraries have tensor core support. So tensor core is a dedicated hardware piece that does really fast FMA, fuse, multiply, and add. And a lot of times the compiler will just handle this for you. It's not usually just like a user opt-in thing because there's no there's no like performance penalty if you don't do it, or correctness. And you can, if you want to make sure that you are using the tensor core, you can use the profilers that we'll talk about tomorrow, just to be absolutely sure. And then this is the CCCL, the core C++ core compute libraries. It's made up of 3 parts: libcu++, and then thrust, which maybe some of you may have heard, and then cub, which is CUDA something unbound, CUDA performance unbound or something. The libcu++ is like, if you imagine modern C++ is the core language plus the standard library, the libcu++ is the standard library variable for CUDA. So CUDA has the core language, and then its new standard library. And then thrust is a parallel algorithm library that is high level and enables user productivity. And then cub is a collection of very fast primitives for use in kernels. So whether that's like device-wide primitives, or block-wide or warp-wide. So this is just a little breakdown of the libcu++. There are 2 different places where you can take from: strictly conforming set to the C++ standard, and then a conforming extension set. The non-strictly conforming section has some fun features where the team is able to do some backporting from standard features to older versions, like C++ type traits, which is a C++ 17 feature, to C++ 14, or C++ span, which is a 20 feature, available mostly in C++ 14. Not expecting you to just read this and know what's happening. Just for use, if you want to download these slides, you can see how it's a pretty small piece of code, but it's using thrust, cub, and libcu++. It's using cub in the kernel, which is the top section, for a block reduce, and it's also using the libcu++ atomic add. And then on the host side, it's using thrust for the device memory, just as the device vector. I'll leave this for your viewing for later, but it started with just atomic and type traits, but there's a big team behind this, and they're very interested in adding as many features as they can. I think this slide might even be a little old because it only goes up to 11.3, and I think libcu++ 2.0 has been implemented in CUDA 12, but then there's also some feature stuff. So just a few CUDA 12 highlights. CUDA 12 is primarily a place where we are setting up what we see as the future for our Grace Hopper. Grace is the CPU we have coming out, and then the Hopper is our H100. But there are some interesting things that apply to older GPUs. Like there is updates to dynamic programming, which is not necessarily new in itself. The original blog that described dynamic programming in CUDA is like 10 years old. But there are 3 new ways to launch a child kernel: per thread stream, fire and forget, and then tail launch. Each are pretty complicated, so I've left the doc and you can ask me questions about them. Lazy loading was a feature in 11.7 and then upgraded in 11.8 and 12. When you load a library like kublas, you're loading in all of the kernel functions onto the GPU and the host memory. And there's something like 10,000 kernels in it, plus probably. So lazy loading is a technique where it only loads into functions as you call them, so it can be a big save for memory and loading time. The only caveat is if you have a very latency sensitive application like real-time graphics or something, might not be the best, because the first time you call a function, there's a little bit of latency. But overall, for like 95% of applications, it's a good save. And then with CUDA 12, we have C++20 support for conforming host compilers. And that is all NVIDIA C++ compilers after 22. And then we also have a suite of profilers, but I'll leave that for tomorrow. So yeah, I'll be in a breakout room if you have any questions. It'll be pretty informal. And I have a few examples for StudPar if you want to try those out. And yeah, answer any questions if you have any.
Thank you, Matt. Are there any questions for him?
Hi, I'm Corey Adams from Argonne National Lab. The NVIDIA HPC toolkit does not ship with cuDNN. Is there any reason why NVIDIA doesn't do that? And would you consider changing it to include it in your math libraries?
That's a great question. I do not know personally why, but I can definitely ask and get you an answer.
Any more? You will be during the hands-on, right? You will be doing, okay, so he will having a hands-on after we have a launch talk, and then we have another talk, and after that is a hands-on session. With that, I want to thank Matt and all the speakers for the morning.